Hello, I welcome you all in this course on steam and gas power systems, and today we will discuss about the Rankine cycle. Now, topic to be covered in this lecture are first law for open system, Carnot cycle, Rankine cycle, performance parameters of Rankine cycle. The first law for open system states that del Q minus del W in an open system is equal to dH plus CdC plus GdZ. CdC is change in kinetic energy and this is change in potential energy, and dH is change in enthalpy. We will take the case of turbine first of all. So, turbine is a device where steam is passed at high pressure, inlet is high pressure steam and outlet is low pressure steam or gas, and this turbine produces power, shaft power. Now, in this case delta Q is 0, process is supposed to be in the ideal case an isentropic process, so there is no heat interaction with the surroundings. The change in potential energy is also considered 0. If there is no change in inlet and outlet velocity, or there is an insignificant change in inlet and outlet velocity of the fluid, then this is also 0. So, minus delta W is equal to dH, and dH is nothing but H2 minus H1, or we can say the turbine output is equal to H1 minus H2. It means the output we are getting, work output we are getting from the turbine is the difference of enthalpy at inlet and enthalpy at the outlet of the turbine. Now, the second thing is nozzle, because before the turbine, in order to increase the velocity of the steam, the nozzle is used. It is fixed before the turbine, or in some of the cases, in many of the cases, it is part of the turbine itself. So, nozzle is a very important part of steam power generation system. In case of nozzle, again if we write del Q minus del W is equal to dH plus CdC plus GdZ. So, nozzle is nothing but a passage of varying cross section in order to increase the velocity of steam. Again, now state 1 to state 2, there is no heat transfer. This process is also considered to be isentropic process. So, there is no heat transfer with the surroundings. Nozzle does not produce any output, there is no shaft output of the nozzle. So, this is also 0. Change in potential energy in most of the cases is 0. So, dH is equal to minus CdC, or H2 minus H1 is equal to minus C2 square minus C1 square by 2, or we can write that H1 minus H2 is equal to C2 square minus C1 square by 2, right. In most of the cases in the nozzles, it is assumed that the inlet velocity is tending to 0, it is negligible in comparison to the outlet velocity. So, C2 can always be taken as under root of 2 times H1 minus H2. Now, this is another second application. Now, third application can be in case of pump. Now, pump is also used in a steam power plant, just to pump the feed water, and here also we can make use of first law for open system. dH plus CdC plus GdZ. So, this is 0, right. In pump, it is again it is considered to be an irreversible adiabatic process or isentropic process. This is 0, and change in kinetic energy is also considered to be 0. So, dH is equal to minus delta W, because in a pump work is done on the system. So, work consumed by the pump is W, and this is equal to H2 minus H1. Enthalpy of fluid outside the pump and enthalpy of the fluid which is entering the pump. So, and this is enthalpy of fluid which is entering the pump, this is enthalpy of fluid at a, this is state of, this is the state 2 and this is state 1, and H2 minus H1 will give the work consumed by the pump. Now, after this first law for open system, we will take up Carnot cycle. Now, in a Carnot cycle, there are 4 processes. If we show a Carnot cycle on PV diagram, there are 4 processes. There are 2 adiabatic processes and 2 constant temperature process. So, these processes starting from state 1 to state 2 is adiabatic, state 2 is here, and state 2 to state 3 is temperature constant, and then 3 to 4, this is 4. So, 3 to 4 is again adiabatic process. Now, a cyclic process where alternative processes are constant temperature and constant entropy. Now, this process has to take place in minimum possible time if we have to maintain this process as isentropic process. So, this process 1 to 2 has to be very fast. Now, process 4 to 1 it is constant temperature process. The constant temperature process has to be very slow, because in this process there is no change in internal energy. Now, if we transform this Carnot cycle on temperature entropy diagram, it is going to be a rectangle, because temperature is remaining constant from process 4 to 1, and 1 to 2 there is isentropic process, it is going to be a vertical line on temperature entropy diagram, 1 to 2. Now, 2 to 3 is again constant temperature process. So, this is, let us say, TL and this is TH, and we get state 3 and state 3 to state 4. Now, if we use gas as a working fluid here, then there is a problem I mentioned earlier, because alternative processes have to be very fast and very slow. So, that is very difficult to realize in practice. Now, we can go very close to this Carnot cycle if we use the fluid and where in process 4 to 1 phase change takes place, because when the phase change takes place during heat addition, then temperature remains constant. So, if we ensure that process 4 to 1 and 2 to 3 phase change takes place, then we can come very closer to the Carnot cycle. So, instead of using a ideal gas, if steam is used in a Carnot cycle, now if steam or water is used as a working fluid in a Carnot cycle, then we can have, this is a saturation line, x is equal to 0 and this is x is equal to 1. Here the water vapor is dry and saturated, and this is saturated liquid. So, when the liquid starts boiling, the temperature will remain constant. So, here we can realize process 4 to 1. For process 1 to 2, isentropic expansion, entropy will remain constant. And again for process 2 to 3, we can condense the water vapor. During condensation, the heat will be rejected and the temperature will remain constant. And at state 3, we can compress this mixture of, because in this region it is going to be a mixture of water vapor and the liquid water. So, the process 2 to 3 will remain in two phase region where temperature remains constant. So, this is how we can come close to the Carnot cycle, but there are again there are problems in this system also. The first problem is when to take up, because all these processes will be taking in different physical entities, because process 4 to 1 will be taking place inside a boiler, right. So, this is state 4 to state 1. From 1 it will go to a turbine, 4, sorry, this is 1 and this is 2, and from 2 to 3 shall take place inside a condenser, 2 to 3, and 3 to 4 shall take place inside a pump. So all the processes, all these processes, they will take place inside different entities, not a single entity. So now the question is, when the process 2 to 3 is complete here in the condenser, then vapor has to be removed exactly at this quality from the condenser. Otherwise, we will not be able to realize the state 4. Second thing is, we have compressors which can compress the gases. We have pumps which can increase the pressure of the liquid, but we don't have any device which can compress the mixture of liquid and vapor, because the moment you start compressing this mixture, the condensation will start, and device will not work at all with high efficiency. We can develop a device, but the efficiency will be very low. So this solution is not workable because we have a problem from state 3 to state 4. The second thing is, if you look at the length of this cycle, stroke of this cycle, this is this much, right? And area is the work or the energy produced in the cycle is only this much, area of PV diagram. So if I am able to develop a Carnot engine, it may be a very efficient engine, because no engine can have efficiency than an engine working on Carnot cycle between two temperatures TH and TL. But in that case, the engine will be highly efficient and bulky. So an engine working on a Carnot cycle may be of this size. If I take a gas engine working on a diesel cycle, may be of this size, right? So not only efficiency, size of the engine is also important. Now here, let us go back to this issue. This issue is important because in process 3 to 4, a lot of energy will be consumed if we are able to make any device which can compress this mixture to this saturated liquid state. So Rankine made one modification. He made one modification. Instead of condensing mixture up to state 3, mixture is condensed up to state 4. Sorry, state 5. This is state 4, so state 5. Now entire vapor is converted into the liquid. This is saturated liquid. And when entire vapor is converted into the saturated liquid, now this liquid, the pressure of this liquid can be increased with the help of a pump, and we get state 6. This is temperature and this is entropy. And after attaining this pressure, this 6, the liquid is sent to the boiler for heat exchange, and process 6 to 1 takes place inside a boiler. So now this Carnot cycle is modified as Rankine cycle. If we show this cycle on PV diagram, it is going to be like this. Sorry, on temperature entropy diagram. This is going to be like this. State 1, state 2, state 3, and then state 4 and state 5. The moment the vapor is condensed up to state 5, the volume is reduced drastically. For example, at atmospheric pressure, if we take saturated steam, and if we compare the volume of saturated steam and saturated liquid, the volume of saturated steam is approximately 1600 times greater than the volume of saturated liquid. It means if we take 1 liter of saturated liquid at atmospheric pressure, if we convert entire this 1 liter of water into the steam, we will be getting approximately 1600 meter cube of steam per kg of or per liter of water. And so the change in volume is very high. So when all the steam is condensed in a condenser, the volume of the gas is reduced or fluid is reduced drastically, and it is very easy to compress, because here the work consumed will also be less, because it is going to be VDP from state 5 to state 6. Now, this high pressure liquid will be sent to the boiler, and where heat exchange from state 6 to state 4 and state 4 to state 1 will take place. From state 1 again the fluid will enter the turbine and the work will be produced. Now, performance parameters of Rankine cycle. In order to find the performance parameter, one is efficiency of the Rankine cycle. Thermal efficiency of the Rankine cycle. Thermal efficiency of the Rankine cycle is output of the turbine, that is the work we are gaining, and work done in the pump, work consumed by the pump. So, it is H1 minus H2 minus work consumed by the pump, and often it is insignificant. If you compare this value, it becomes insignificant, and sometimes it is neglected also, divided by heat given. This is H1 minus H6. This is amount of heat given to the system, and this is work output of the system. Now, if we take thermal efficiency of Carnot cycle, it is going to be H1 minus H2 minus H4 minus H3, because this is significant. Here it is significant, we cannot neglect it, divided by H1 minus H4. Now, I will take one numerical and I will compare the performance of these two cycles. The numerical states a steam power plant operates between a boiler pressure of 40 bar and a condenser pressure of 0.04 bar. Calculate for these limits the cycle efficiency, work ratio and specific steam consumption. Cycle efficiency is thermal efficiency of the cycle. Now, work ratio is the net work divided by turbine work, that is the work ratio. So, here the work ratio can be H1 minus H2 minus WP divided by turbine work, that is H1 minus H2. Now, if you compare the work ratio of a Carnot cycle and a Rankine cycle, work ratio of Rankine cycle will turn out to be much higher than the work ratio of a Carnot cycle. Now, the second one is specific steam consumption. Specific steam consumption is steam consumption per kilowatt hour. This also we can derive from these values. So, in order to start this, we will take first Carnot cycle. So, in case of Carnot cycle, the pressures are 40 bar and 0.4 bar. Now, temperature, this is TH and this is TL. So, TH, or we can take T1 and T2 also. In some of the books it is taken as T1 and T2. So, T1 is saturation pressure at 40 bar, because the pressure is 40 bar. So, at this pressure accordingly saturation temperature will be taken. These temperatures you can take from the steam tables. You purchase steam, there are number of steam tables available in market, and you purchase any of these steam tables, because steam table will be frequently required in this course. And take the steam table which has Mollier diagram also, because we will be using, sometimes we will be using Mollier diagram also. So, from steam table there is a table for saturation properties, where for every pressure you will get the saturation temperature. So, from that steam table I have taken at 40 bar pressure, the saturation temperature is 250.35 degrees centigrade. Now, if I convert this into the Kelvin, then it is going to be 523.3 273.35 Kelvin, because you add 273, you will be getting temperature in Kelvin. Now similarly, you can calculate the temperature T2 at 0.04 bar. It is 28.96 degrees centigrade, and if you convert this into the Kelvin again, you will be getting 302.11 Kelvin. So we have two temperatures, and I hope all of you can find the efficiency of the cycle, because efficiency of the cycle, Carnot cycle, is 1 minus T2 by T1. This 1 minus T2 by T1 will give you efficiency of the order of 42.3%. Now, if I ask you to find the output of the turbine, now output of the turbine will be work. Now, this work is net work. So, this net work involves the work developed in the turbine minus work done in compression. So, this is the net work is H1 minus H4 heat supplied multiplied by the efficiency, and the net work you will get H1 and H4 you can take from the steam table. The at 40 bar pressure, the enthalpy of saturated vapor and enthalpy of saturated liquid. So, H1 and H4 will give you, you will get the net work as 724.7 kilojoules per kg, right. Now, turbine work, suppose I want to find the turbine work, then turbine work is H1 minus H2. Now, H1 we can take from the steam table, saturated enthalpy of saturated vapor, H1. This we can take from the steam table, but what about H2? H2 is not given in the steam table. So, in order to find H2, we will take S1 is equal to S2, it is a property of this process, S1 is equal to S2. S1 we can take from the steam table. So, S1 is 6.0696 kilojoules per kg Kelvin, and that S1 is equal to S2. Now, S2, we know in this process, because it is a constant pressure process and 0.04 bar pressure. So, for 0.04 bar pressure, we know the entropy of the liquid and entropy of the vapor. So, we can always take S2 is equal to SF plus X Sg minus SF. Now, from here we can calculate the value of X, and in this case the value of X is 0.701. Now, once we have the value of X here, X is the quality of vapor. Once we have quality of vapor at state 2, we can find H2, because H2 is HF plus X Sg minus Hg minus HF at this pressure 0.04 bar pressure. So, from here we will get the value of H2. Now, we have value of H1 and H2, we can find the turbine work as H1 minus H2, and in this case the turbine work is 974.4 kilojoules per kg, right. Net work was 724.7 kilojoules per kg. This was the net work, and this is turbine work. So, difference of these two works will give the energy consumed in the process 3 to 4. So, energy consumed in the process 3 to 4 is equal to, that is work of the compression is 249.7 kilojoules per kg. So, this is the amount of energy is being consumed, in the process 3 to 4. Now, the work ratio is 724.7 divided by 974.4. This is the net work, this is the turbine work, and it is going to be 0.744. And specific steam consumption is equal to net output is how much? 724.7. 724.7 multiplied by 3600. That will give the specific steam consumption. It is going to be 4.97 kg per kilowatt hour. So, we are getting all the values: efficiency, work ratio, and specific steam consumption in case of Carnot cycle. Now, this is in Rankine cycle, this vapor is completely condensed, pressurized, and then you get 5, state 6, and then from state 6 heating takes place. We can get enthalpy at state 5, but what about enthalpy at state 6? Because heat added is going to be, here in case of Rankine cycle, heat added is going to be equal to H1 minus H6 work in the pump is S6 minus H5, but the issue is how to find S6. Work is pump is S6 minus H5, and work in pump is also minus V dP from state 5 to state 6. In liquids, if you pressurize liquids, the change in specific volume is insignificant. That is why on a PV diagram, if you look at the PV diagram of liquids at a constant temperature, this line is almost a vertical line at a constant temperature, and then it goes like this, and then again it goes like this. So, this can be taken as constant, and dP is the pressure difference. So, we can always take specific volume at state 5 multiplied by P6 minus P5. I have done this calculation, and the specific work of the pump is approximately 4 kilojoules per kg. It is almost insignificant if you compare the output of the turbine. In case of Rankine cycle, the work of the pump or pumping work was coming out to be 249.7 kilojoules per kg. So, you can compare the energy consumed in the Carnot cycle and energy consumed in Rankine cycle in pumping the fluid. Now, again, in order to find the efficiency of the cycle, so thermal efficiency of the cycle is going to be H1 minus H6, H1 minus H2 minus pump work divided by H1 minus H6. Now, we have all the values: H1, H2 is with us, H5 is with us, add the pump work, you will get H6. So, using this equation, the thermal efficiency of the Carnot cycle comes out to be 36.6%. It is less than the Carnot cycle. In Carnot cycle, we were getting 42.3%. Here we are getting only 36.6%, but at the same time you can see we are getting more output. Work output is in this cycle is H1 minus H2. It is same as was in the case of Carnot cycle minus work of the pump, and where here work of the pump is very less, only 4 kilojoules per kg, and it comes out to be 970.4 kilojoules per kg. So, in this Rankine cycle, the efficiency is lower than this, but we are getting more output in this case, and this is more practical cycle if we compare with the Carnot cycle. Now, I end my lecture here. In the next lecture, we will see how we can improve the efficiency of a Rankine cycle.